Okay, this is day 6. I will scroll down and have some of the homework answers. There's a bunch of them. So after I leave it up for a little bit, I'll scroll down and you can see the rest of them. I believe there was one section where you had to use each of the different tests once. So there might be some variation as to which ones you chose to use where. But we'll see those when you go through the worked out solutions. So while you are checking these answers, the sub should be passing out the notes packet for today. Since our next problem set won't be due till the Friday after we are back from break, I'll just wait and pass that out to you once I am back in school, which hopefully will be tomorrow. Leave these up for another minute or so. Remember, once I start flipping through, I'll talk about each of the worked out solutions a little bit. And then I'll let you know when I'm going to flip the slide. If you need the sub to pause it there so you can have a few more minutes, well, not a few more minutes, but another minute or so to fix anything on yours, just shout out for them to pause it. All right. So most of these we're looking at limit comparison tests. So here's our original series. We could compare it to 1 over 3 to the n. So when we divided them here and did the limit as n approaches infinity, we got infinity over infinity, which told us L'Hopital's. Our derivatives then, 3 to the n times ln 3 for both, well, those all divide out, and we just get 1. So that is a positive finite value, okay, greater than 0. That means our original series will do whatever the nice one does. We know the sum of 1 over 3 to the n. We can rewrite it as a geometric, where a great absolute value of r is less than or equal to 1, so therefore it converges. And we can then say our other series will also converge by the limit comparison test. I'm going to go ahead and switch. Yell out pause if you need the sub to pause it. So the square root of n squared, essentially we can compare this to 1 over n. So if we divide those two with your keep change flip, you end up down here, and we do our limit as n approaches infinity. Well, the square root of n squared minus 4, that's going to take on the same value as absolute value of n as n goes to infinity. But because we're going to infinity, n is just a positive, so this will eventually give us a 3, which is greater than 0. So that means we can use the limit comparison test. Our nice one diverges because it's a p-series where p equals 1, or you could say p-series where p is greater than 0, less than equal to 1, or you could say diverges because it's a harmonic series. Any of those would be fine. So therefore, our conclusion up here, our limit comparison test, our original series diverges. Next one, our gap between our degrees is 3, so we'll use 1 over n cubed. Notice for each of them, I'm just showing, yes, they are greater than 0, because those were conditions for us to be able to do these. But when we divide them, we end up, as n goes to infinity, getting 2/3, so we can use limit comparison test. Our nice one converges, p series with p greater than 1, therefore our original series also converges. Whatever the nice one does, the one we're looking at does the same. 21, that's really an n squared on the bottom, so we'll use 1 over n again. Divide it to your keep change flip, so we'll get n squareds both top and bottom, so ratio leading coefficients is just 1. So that is greater than 0, so our limit comparison test applies. We know that the 1 over n diverges. A couple different ways you could describe that. Then we know by limit comparison test, our original one also diverges. I'm going to switch. If you need to pause, y'all pause. So as n goes to infinity, the bottom is basically going to be an n squared because the square root part will be absolute value of n, but that'll be the same as n because we're going to infinity. So it's like we have an n squared on the bottom right now. So we want to compare that to 1 over n squared because that'll be the difference between, or the gap between our degrees of top and bottom. So when we divide, we can do that analysis on the bottom. What I did from that first one here to the second one here is I divided out one of the n's already. You don't have to do that. You could have left this as n squared on top and n absolute value of n and then just had these both be n squared. You get the same thing. I just thought that neatened it up a little bit. But anyway, that's greater than 0. 1 over n squared converges because p series, p greater than 1. So by limit comparison, our original must converge. All right, so this one, so this one we're going to use 1 over 2 to the n minus 1 because our degrees of n were already the same. So now when we divide, do our keep change flip, the 2 to the n minus 1's divide out. And then, now I showed a L'Hopital step here. You didn't need to show this L'Hopital step because we know that leading coefficients from the same degree is just going to give us 1. So we could have jumped right to there. But you can do that if you wanted. So then we got to see, well, what is our nice one? That can be rewritten as geometric, where absolute value of r is less than 1, so it converges. So by limit comparison test, our original converges. Oops, sorry. I'm going to switch, so if you need to pause, y'all pause. So as n goes to infinity, the denominator is going to be an n plus an absolute value of n, which is kind of like saying 2n. So basically we need an n on top, which is why we'll use 1 over n. So if we divide, we get 5n over that denominator. As n goes to infinity, again, it will be like having n plus absolute value of n, but since we're going to infinity, that's like n plus n, so we have 2n. The n's divide out, so that heads to 5/2, which is greater than 0. So that means our original series will do the same as our nice one. So we've got our harmonic there. It's a couple different ways you can say why it diverges. And therefore, our original one also diverges. I'm going to change the slide. So this one, there was probably some difficulty on. So what we're going to do here is we're going to use 1 over n because it matches the inside. So we had to be pretty clever. When we do our limit as n approaches infinity, we're not going to do keep change flip. What we're going to do is we're going to rewrite the limit. N going to infinity is the same as the inside of the sign and the denominator going to 0. So we could rewrite that limit as being the same as saying limit as x approaches 0 of sine x over x, which we've seen many times before is just equal to 1. So this one's a little different. We had to use some prior knowledge and be a little clever to get to that point. 1 over n diverges harmonic, so we know our original one diverges by limit comparison test. All right, so here are the ones where you had to use each one at least once. So there's a chance you might have used some of them in different spots, but you had to have them each in one spot. So in 29, I noticed we could divide out an n to the 1/2, leaving us 1 over n to the 1/2. So that just diverges by p series. In 30, that was geometric, so you're converging because absolute value of r is less than 1. So in 31, seemed like a candidate for direct comparison because the denominator is a little bit bigger than 1 over 3 to the n. That means that our original series would always be smaller than our nice one of 1 over 3 to the n. Well, because 1 over 3 to the n is the same as 1/3 to the n, we know that converges by p series. So we know everything smaller than it must also converge, which our 1 over 3 to the n plus 2 is smaller. So we can say that converges by direct comparison test. We'll switch the slide. So 32 I thought was a good candidate for limit comparison. So I compared it to 1 over n squared. When you divide, do keep, change, flip, n goes to infinity, you get a positive finite number, 1/3. Our nice one converges because p series with p greater than 1. So therefore, our original must converge by limit comparison test. So in 33, the limit as n goes to infinity of our original is not 0, so we know that automatically diverges by the nth term test. 34, we've got subtracting of terms, so that kind of leads itself to telescoping. There's only the 1/2 in the front that didn't wipe out, so we'd have one thing subtracted on the end, so that approaches 1/2 and converges by telescoping. Oops, sorry. I'm going to switch the slide. If you need to pause, see, I'll pause. I used the integral test. It was positive, continuous, and decreasing. When you do your integral, you can do a little u substitution on the inside of that denominator, correct with a 1/2. To your antiderivative, I adjusted my bounds to 2 and b squared plus 1. Subbed back in. As b went to infinity, we ended up getting a 4th, so it converged by the integral test. Remember, this does not mean the series converges to 1/4. Okay? In fact, it does not converge to 1/4. It only means that the series also converges. I'm going to switch the slide. So this one we can compare with 1 over n squared. When you divide them to keep, change, flip, as n approaches infinity, we approach 3 because leading coefficients. The nice one is a p series, which is going to converge because p is greater than 1. So by limit comparison, the original must also converge. Okay, so this one, we have one series that's less than another. If A of n converges, then B of n has to diverge. Well, if, say, we knew the big one converged, then we should be guaranteed that the smaller one converges. That's our direct comparison test. But we basically can't know for certain if the small one converges what the bigger one does. So in reality, it could do either. So that's why this if-then statement has to be false. So the example I gave was 1 over n squared and 1 over n cubed. 1 over n cubed is always going to be smaller than 1 over n squared. 1 over n cubed converges, p series, where p is greater than 1. And then b of n, 1 over n squared, also converges by the same reasoning. So you could have had different counterexamples here, but everyone should hopefully add false. Okay, so hopefully you have your notes packets. Today is the alternating series test. It is one of the most popular tests that you will use on the AP exam, partly because it is very easy, both to identify that it should be used and to actually use it. So if you have the option to use this, you pretty much always go for it. So first off, what is an alternating series? An alternating series, we would notice we have a -1 raised to some power. Just two options you have. There's an n and an n plus 1, and that just changes whether the negative starts with the first term or the second term. And then the negative, it switches from negative to positive. That's where the alternating comes from. Now, another way you could get an alternating series is if you have a cos. Say you had a cos pi x. Well, cos of 1 pi would be -1, but cos of 2 pi would be +1. Cos of 3 pi would be -1. So that can be used to generate an alternating series as well. So just keep that in mind. So here's an example of an actual alternating series. So if we go to the next slide, our alternating series test. If you meet both these conditions, then we know the alternating series has to converge. So the first, let's talk about the second one first. Limit as n approaches infinity of an equals 0. Now, let me specify, when we're saying an here, we're talking without the plus or minus. We're talking about the absolute value of the term. Okay, we don't worry about the negative when we're talking about the an's here. So number 2, why I started with it is if that wasn't equaling 0, we would already know it diverges by the nth term test. So that one seems logical. Yeah, if it's going to converge, we already know from previous day that it has to equal 0. So in the top one, what that's really saying is each next term should be less than or equal to the term before it. Now what it says in the parentheses, or for all n greater than m, basically that needs to be true eventually. Because every now and then, maybe like somewhere in the first couple terms, there might be 1 or 2 terms that get bigger for a second just based on the makeup of the expression, and then it starts getting smaller. As long as eventually they keep getting smaller forever, then you can apply the alternating series test. Now remember, a good strategy on any series question, if you're unsure how to approach it at first, is write out several terms, and that might jog your memory of what to do. Okay, that is a good strategy to do anytime you are not sure how to approach a series question. All right, so if we write out a few terms there, we get -1. When we put in 1, we get +1/2, -1/3, +1/4. So our terms are getting smaller each time. Okay, each successive one is less than the one before it. And again, we're talking the absolute value of those. And our term values are going to 0. Then by the alternating series test, this converges. Now, I want you to think about why this might be a surprising result. And hopefully some of you are thinking, well, 1 over n is the harmonic, and we know that diverges. But if you have an alternating harmonic, that actually converges. So the alternating harmonic is a convergent series, but the regular harmonic does diverge. I'm going to switch the slide. If you need to sub to pause it, just yell pause. So here's our next series. If we write out a couple terms, we fill in 1 for n, we get -1. Fill in 2 for n, we'll get a positive, we'll get 2 on top, 3 on the bottom. If we keep going, we'll get -3/5, +4/7, and so on. Each term does appear like it's less than the one before it, because 2/3 is 0.66, 3/5 is 0.6, and so on. But as n goes to infinity, our values are gonna, by leading coefficients, gonna approach 1/2. So alternating series test cannot be used to show convergence here because this diverges by the nth term test. So this is a prime example that you can't just assume those two conditions are going to be true. You have to still think about it. Now, when you list out a few terms, it is pretty easy to see when a series alternates. So that's why this test is pretty easy to identify when you should be looking to do it. And it's a pretty quick check on whether it converges. So that's why it's a popular one. So because this is so easy, we're going to show you one a little bit more challenging thing with this. So another way to show that each term is less than the one before it would be to show that the derivative is always negative. So if we did a quotient rule for x over 2x minus 1, that's what we have here, notice we get this. Denominator is always positive, numerator is always negative. So this derivative is always negative, meaning it must be decreasing all the time. So it wasn't that hard to sub into that top one and see it was decreasing, but if we have something like this on the bottom, okay, it could be a bit easier to tell that it is decreasing all the time. Oops. I'm going to switch the slide. There's nothing you have to write down here, so hopefully everyone's okay. All right, I apparently did not write anything down on these last ones here from last year. So this is just an example to show that sometimes it takes a little while before they start getting smaller and smaller. So notice here they get bigger for a little bit, but now eventually we're getting smaller and smaller. So that does check off number one because eventually they will do it. And the exponential is going to grow a lot faster than the linear, so this will go to 0. So we can say that this diverges or converges by the alternating series test. This one, they're definitely getting smaller and smaller. It is alternating, so checks off. This one is going to approach 0, so that checks off. So this would converge by the alternating series test. So we kind of went through those two quick because I wanted to make sure we got to alternating series remainder. Okay, this is the most popular remainder that you'll do because it's pretty simple. So here is our infinite sum in an alternating series. Okay, we started with -1/1, 1/2, -1/3, and so on. This would represent your partial sum, the Sn. This whole thing is representing the infinite sum. So that means this much left is the remainder. Well, when you are doing an infinite sum, basically each term that you add on is constantly jumping on either side of the infinite sum. So let's say this is the number line here, and this is where our infinite sum is. Well, when you add a term, maybe it gives you a value right here on the number line. When you then subtract the next term, because it is smaller, it is going to jump to the other side of the infinite sum, but should be a little bit closer than before. Because when you get to this one, if we had just added a term, it was adding beyond that infinite sum. So this gap here should still be smaller than what we're subtracting. And then as you add, then we would jump over here. And then as we subtract, it would jump over here. So each time you're adding and subtracting a term, it's basically closing in on the infinite sum. So what that means is each term we're adding or subtracting is going to go beyond where that infinite sum is on the number line. So our distance from the partial sum to the infinite sum must be less than the next term, because that next term is always going to jump to the opposite side on the number line of the infinite sum. So if you want to do your remainder, and we saw this notation with our integral remainder, s minus s infinity. Now the reason we have absolute value bars here is because we're alternating. We just care about the overall. So this is saying it'll just be less than or equal to whatever the next term is. Your next term will always be bigger than and now keep in mind, this is without the plus or the minus. This is the absolute value, the an plus 1. Your next term will always be bigger than the gap, the remainder between your partial sum and the infinite sum. So in this series that was demonstrated up here, if we did the partial sum of our first 5 terms, we'd get negative 47 over 60. So our remainder of this 5th partial sum would be less than or equal to whatever the 6th term is, okay, but without the plus and minus. So the 6th term would be 1/6. So what we know for certain then is that our partial sum is between the negative 47/60ths with the 1/6 subtracted and the negative 47/60ths with the 1/6 added. We know that partial sum has to be within there. Now, this remainder is much easier to do than the integral. It's a lot less work. So this is the one that we see come up actually a lot more. I'm going to switch the slide. If you needed to pause, I'll pause. Now, just like the other ones, we can find how many terms we will need in order to have our remainder within a certain threshold. So we want to be within 0.001 of the infinite sum. So we need to take our calculators out. So if you could please take those out. And we know that the remainder to be less than 0.001 means the next term needs to be less than 0.001. So all we're going to do is in a graphs page. So everyone go to a graphs page. We don't need to worry about the minus, okay, because remember it's the absolute value we're worried about. We're going to take our expression, the 4 over n factorial, and we're just going to think of it with n plus 1 in there. So we're going to want to do 4 over n plus 1 factorial. But we're in a graphs page, so we got to put it in as an x. So you're really going to put in 4 over parenthesis x plus 1 close parenthesis factorial. Now the factorial is with, I think it's the question mark. It's to the right of the letters down on the bottom. So all the letters on the keypad down on the bottom, I believe there's a little question mark there. If you hit that, then the factorial is in there. So now all we do is we go to the table, and in the table scroll down until you find the first one that is less than or equal to 0.001. Now what you have to be careful of is it's going to switch to scientific notation eventually. So 0.001 is the same as saying 1 times 10 to the negative 3. Now when you scroll through, you can have your cursor on the y's column essentially, and it'll show you full written all the way out on the bottom what it is. So we should see that when x equals 6 or n equals 6, that is the first time that it will be below. Now your work that you would show is you would just show a couple in your table. So like you would show at 4, what is it, 5, what is it, and 6, what is it. So I didn't write the y values here, but you should write that on a test. And now this particular question says find n. So it's just our n equals 6. But I have seen questions before that say which term will make the remainder. Make it so the remainder is less than 0.001. If it says what term, you just need to be cautious, and I know this comes up on the review sheet. is if it by chance had n equals 0 on the bottom instead of n equals 1, then the term would be 1 extra than the n we found. So just keep that in mind. I know that comes up on the review sheet. I'm going to switch the slide. And I guess that's it. All right, so you have day 6 for homework tonight, alternating series test.